Hello, this is CS323 Programming Languages, and I'm going to be talking to you in this video lecture about reviewing what we would consider attributes of quality related to a programming language. So, one of the first quality attributes we talked about towards the end of last class was the idea of readability. So you have that in your notes. And second attribute we talked about was simplicity. You also have that in your notes. And the third attribute that we talked about was something called orthogonality. So orthogonality, just to simplify it or kind of create a quick overview of it, it's the idea that you just have a few language constructs, and from those language constructs you're able to pretty much describe all of the data and control statements in the language that you have. And this is really great because it makes it really easy to learn a language if there's just a few statements that you have to work with, and yet the language is just as expressive as more sophisticated language like, say, Java. So the thing I want to talk about next is I want to talk about control statements. So we'll spend a little more time dealing with that. Okay. Oops. Trying to get to know this. All right, so control statements. Now, first of all, I would ask you, without me spilling the beans, to think about can you give me an example of a control statement? All right, so if you're watching the video, hit the pause button and think about one or two examples of control statements, and then I'll spill the beans once you hit play. So hit that pause button. Did you hit the pause button? I hope you did. Okay, so I'm going to spill the beans. An example of a control statement would be something like an if statement, right? If you have a set of sequential code that's executing and you run into an if statement, if the Boolean expression evaluates to true, you're going to execute the code in the if block. If it evaluates to false, you won't execute the code in the if block, and that way you control the flow of execution of your program. All right, so prior to the late 70s, the primary mechanism for control flow that involved repetition was something called a go-to statement. And most of you have never seen this, which is actually a good thing. But I'm going to write some code, and I want you to look at the code and then tell me what you think this piece of code does. So here we go. I is equal to 1. Then I'm going to have something that's a label. So loop 1. And then an if statement. If I is greater than or equal to 20, go to out. And then I'm going to have something right after that that says loop 2. And that's going to have an if statement as well. If sum is greater than 100, go to next. And then I'm going to have some more code under that. Sum plus equals I, go to loop 2, and then next. And then under next, I'm going to say I++. And then go to loop 1. And now, still getting to know this system here. Whoops. There we go. Just wanted to move that up a little bit. And then right underneath that next, I'm going to say out. Okay. And now what I want you to do, that's actually great. Okay. What I want you to do is take a look at this and see if you can tell me, or tell yourself, what you think this code is doing. So imagine you have a language and the only thing you've got in the language for controlling repetition is this goto statement. All right, and by the way, when it says goto and it's followed by a label, for example, right here, goto out, what it means is that you're going to jump from the current line of code to the statement out. All right, so again, using the awesome power of pause, I want you to pause the video and figure out what this is doing. So it might take a couple minutes to think about it. If we were in class, I'd be quiet. You guys would be scribbling notes and trying to figure out what this means. So try that out. Okay, I'm going to assume you tried the exercise to figure out what this is. What this really is a for loop. I mean, we can represent this as all this code, all that complexity as a for loop by doing this. For I equals 1, I is less than 20, I plus plus. And then inside the for loop, we're going to say while sum is less than or equal to 100, sum plus equals I. So what's happening here is we're continually adding up the numbers and we're adding numbers into sum as long as sum is less than or equal to 100. So as the for loop executes, I starts at 1, we add that, we add 1 to sum, and we add 1 over and over and over again until sum gets to be the value of 100. And then the for loop executes again, and not much really happens with the while loop, and then the for loop executes again, and again, and again, and again, and again. And the for loop doesn't stop executing until we get I equal to the value of 20, in which case it executes. So really, the inner while loop only executes when I is 1, and it continually increments sum until we get sum equal to the value of 100. Okay, so clearly goto statements are not easy to work with. They're not easy to understand. In the early days, as people were transitioning from goto statements to for loops and while loop type constructs, it was hard for people to let go of the goto statements, but I think over time programmers realized that code looked a lot clearer with a for statement or a while statement in a programming language. You know, the holdover, the attraction of the goto statement was it was very similar to exactly the kind of statement you would use in assembly language to control repetition in your program. So I would argue that, you know, the for loop and while loop is kind of influences readability. All right, so let's go on to another topic here. or another characteristic of a good programming language. So this is good syntax. Is there good syntax in the language? So there's a lot of different components of syntax. So one example might be identifiers. And here I'll give you an example. In the programming language BASIC, the early versions of BASIC, kind of stuff that Bill Gates worked on when he first started cutting his teeth when he founded Microsoft, variables or variable identifiers were only 2 characters. Can you believe that? So, you know, you could have a variable x or a variable y or a variable xx, but you couldn't have a variable Bob. In Fortran 77, which you guys are going to be programming with, variables are 6 characters max. So that's not so great. And in fact, you can run into a lot of trouble with Fortran 77, because if you create 2 variables with the same name for the first 6 characters, but then they differ after the first 6 characters, as far as Fortran's concerned, they are the same exact variable. So you can get syntax errors in your code as you try to use a variable of one type with the first same 6 characters as a variable of another type. So another thing you have to watch out for, or good syntax, revolves around keywords. So my question for you guys is, what the heck is a keyword? Can you tell me what that is? So pause the video again for a second and see if you can think about what is an example of a keyword. So pause it. Alright, I'm going to assume you've paused and thought about what a keyword is. So examples of a keyword might be something like while, or class, or for. That would be true in Java. So these are reserved words that you can't use for anything else. Well, in Fortran 77, there's almost nothing that's reserved as a keyword that you can't reuse for something else. So for example, integer, if equals 42. So if in Java is a keyword, it's a reserved word, you can't use it, but in Fortran 77, it's not. It is, you know, it is something that you'd use in an if statement. You say if, but you could also define if to be a variable. So that can make for very confusing code and syntax errors that might crop up that ordinarily don't make any sense. All right. Another aspect of good syntax is that syntax should imply semantics. So what do I mean by that? Well, that means if you look at code and you look at the syntax of the code, the syntax itself is giving you a lot of clues as to what the code is doing, even if you've never seen that code before. So I'm going to give you an example of that right now. See, I'm going to see if I can pause this. I don't know if I can do that. I guess not. So hang on, I'm going to bring something up here. All right. So what I want you to do is, whoops. hang on here. Where is that? Here we go. Okay, I'll move this out of the way. Try one more time. There we go. So syntax should apply semantics. So this is a language that you've never seen before. It's called COBOL, and believe it or not, there's still a lot of code out there that's been written in this extremely verbose language. And the goal of the developers of COBOL is they wanted something that was a lot like English. The syntax of the language is a lot like English. And so you have to do a lot of extra typing. It's very verbose, but it's pretty easy when you look at the language to figure out what the program is doing. So there's a section in here that's called data division. All right, and so this is declaring a bunch of variables, num1, num2, result, and operator. And then there's a procedure division, which is dealing with code that's doing computation. And the name of this method or routine is called calculator. And then this thing says perform 3 times, so that means that we're going to execute this code, this chunk of code 3 times. And the chunk of code is going to be executed 3 times indicated by the indentation. So there's an indent that occurs here, and the indent ends here, so it's this chunk of code right here that's going to be performed 3 times. And then we display enter first number, accept num1, enter second number, accept num2, enter operator plus or multiply, accept operator, and then we have an if statement that says if the operator is plus, then add the numbers giving result. If the operator is multiply, then multiply the numbers giving results. And then we display result is result. So even though you guys have never seen COBOL before, you could easily, just by looking at this syntax for this language in this sample code, got a pretty good idea of what the program is doing. All right, so let's get back to this. All right, so syntax should imply semantics. In addition to control constructs, another question, and syntax, another question you want to ask is, does the language have good process abstraction? And to answer that question, I've got another slide to show you. It's actually in the same group here. So which of these chunks of code would you prefer? Look at the chunk of code on the left and look at the chunk of code on the right. They're equivalent to each other. And I guess the question I'd ask is, what is going on the left that's kind of silly compared to what's going on the right? So hit pause for a second, take a moment to look at these two, and think about what's going on, and then I'll spill the beans. But you have to try and do a little work to figure this out. Otherwise, this is really boring because you're sitting here watching this video and listening to me go blah, 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 blah. All right, so hit pause. All right, I'm going to assume you hit pause, and now what I want you to do, what I'm going to say is, spilling the beans, is on the left, what you see is 3 chunks of code that all do basically sort. So the first chunk of code sorts array section A, the second does section B, and the third does section C. On the right, what we're doing is we're encapsulating or abstracting away the sort into a method called sort, and then we just call sort on, oh, it says section A, but it really, I see there's a little syntax error there. So we're sorting section A, we're sorting section B, and we're sorting section C. Now, clearly, the sort on the chunk of code on the right is preferable to the chunk of code on the left. First of all, just simply from readability standpoint, but also from a maintainability standpoint. If there is a syntax error, not a syntax error, but a logic error in your sort, you are going to have to fix that logic error at least 3 times, right? For the 3 sorts that appear in the main program. And you might correctly fix it in one of the sorts, but mess up the fix in the second sort, and then correctly do it in the third sort, and you could end up chasing the same bug around and around and around in repeated chunks of code. So there's definitely an advantage using process abstraction to make your code more readable and reduce bugs. Makes it easier to fix bugs if you have one. And it also is easier to write because you only have to write this chunk of code once. Another advantage of process abstraction is the whole point of abstraction. Like, one of the goals of abstraction is to hide details, and that allows you to think in a top-down fashion when you're going about solving problems. And I said this to the freshmen, when I usually write code, what I do is I write a main program that acts as an outline for my solution to the problem. And the main program just consists of a bunch of method calls, and I don't even know what the methods are going to do. I just write the names of the methods and what I think the argument should be, and then later I fill in the details of those methods when I write the code for each method. That's kind of nice because when you think top down, you don't have to worry about all the details at once. So all of that goes into process abstraction. All right, let me get back to that here. Okay. So it makes it easier to write. It makes it easier to read. Reduces bugs. It makes it easier to fix a bug. And we hide details in the process abstraction, and it's compatible with a top-down design approach, where top-down design is you think about the big picture and the details get filled in later. And like I said, that's how I build my main programs. All right. All right, what do we want to talk about next? Let's talk about data abstraction. So the ability to have data abstraction in a programming language is really important too. I mean, if you consider this binary tree here, okay, it's got a couple of branches on it. Now, if I gave you a language which had no references and no dynamic storage, how would you go about representing this binary tree? Right? You don't have the ability to have references like you do in Java, and there's no dynamic storage, so you can't say new to create a chunk, basically to create a node. So think about that for a second. I'm saying here's a language, there's no reference ability, there's no dynamic storage ability. How would you describe this binary tree in some kind of data structure? Oh yeah, hit pause. Did you hit pause? I hope you hit pause. Please hit pause and try this, for the love of God. All right. I'm going to assume you hit pause. So the answer to this is that you're going to have a couple of arrays. You're going to have one that takes care of the node value, and stores that in the array. You're going to have one that's in charge of the left, the array slot that's going to have the array node that appears to the left of the current node, and another array that takes care of the position of the array node on the right. So to give you an example here, let's say the first node value, this is the root, the first one has the value of 3 in it, okay? And the node on that, so we'll say this is position 0, this is 1, 2, 3, 4. So, and you know, the node values can be whatever you want. So at position 0, we have a node value of 3. So there'd be a 3 in here. And then the node on the left is going to be the node at position 1, and the node on the right is going to be the node at position 2. So the node on the left is going to be this position, is going to be the node at position 1 in all of these arrays. Alright, so given that that's true, I want you to try and fill in, and let's just assume that, I'll just make this a little bigger for the sake of argument. Let's assume that at position 1 we have 10, okay? So at node 1, I'm sorry, we have the value of 10, a node value of 10. So I want you to fill in everything in the next set of rows in these 3 arrays, or the next row in these 3 arrays. Alright, same thing, hit pause, fill it in. Let's see what you get. I hope you hit pause. I really hope you hit pause, because I'm going to spill the beans. Alright, so you're going to put a 10 here. You're going to put a, I guess we don't really have anything to put in for left and right, so I might put a -1 and a -1, because there's no left and right branches here. There's no left or right branches here. Alright, try it for the next one as well. Same thing, hit pause. This is a better example. Okay, and I'll put a node value in here for 2. Make that big enough so I can write something. I don't know. It's pretty hard to use the iPad to do this. Let's put a 9. Okay, you can barely see that. There's a 9 in there. Alright, so fill in row 2 for these arrays. Hit pause first. Alright, so you should be putting a 9 in here, and then the array, the node on the left is going to be node 3, and the node on the right is going to be node 4. And when I say 3, what I mean is that's row 3 in this set of arrays, and we've got row 4 on the right in the set of arrays. Alright, what a pain that is to fill that all in and manage all of it. It's much better if you have a language that does have the ability for references and dynamic storage. So in C++, you'd have something that looks like this. Class, node, open curly brace, int value, so that's going to store our value. And then you say node reference, left, and node reference, right. And pictorially, if I wanted to create a node, what I would do is I would say, like let's say I wanted to put in that first node. Pictorially, it's going to look like this. Okay, and, oh, is it? I can't, let me go back for a second. Oh, it's going to have the value of 3. All right, so I got the value of 3 here. 3. Oh, that's cool. I'm going to change my color. I like blue a lot for this kind of stuff. I wonder if I can make the pen tip smaller. I'm going to do that too. Okay. All right. And I'm just going to set this node up over here. So I've got 3, I've got 10, and nothing's going on here. So to get this all to work, I might say something like this. Node star root equals new actually I might do this equals malloc size of node, and I'd say node star malloc size node. So malloc is C++'s way of carving out a chunk of memory. So when you see malloc, you have to give it a specific size. So we want the size of the structure node, which consists of some space for an int value, a space for a node left, and a space for a node right. And then we would do the same thing for, we'd say if I wanted to fill in the, let's just do the left, some memory for the, well, we'll fill this in. So then I'd say root dereferencing root value equals 3, and then I'd say root left, that's an arrow by the way, left equals node star malloc size, oh it's size of node. Okay, and whoops, sorry. And then what I've done here in the bottom is I've allocated space for the left node, which is going to end up having the value of 10. All right, that is much nicer than that array representation because I can add and subtract as many elements as I want. If things disappear, it's easier to, if a node disappears, I have to rearrange a set of nodes. It's much easier to rewire the references to nodes than it is to try and get all that to work in an array. All right. Now, the last quality that I wanted to talk about of a programming language, the last important quality, is, it's interesting. I wonder if this is all one, no, hang on. Okay, there we go. The last quality I want to talk about is the idea of cost. How much does it cost to work with a particular programming language? And so I want you to try a little exercise here and see if you can come up with just a couple of different ideas about what would be involved in the cost of working with a particular programming language. So again, hit pause, put on your thinking cap, and then I'll spill the beans. Hoping you hit pause. Really hope you hit pause. I really, really hope you hit pause. Okay, now I'll spill the beans. So there's cost associated with a lot of different aspects of working with a programming language. So one thing is training. That's kind of an important feature, right? There's how much work is involved in creating programs using the language. You know, if it's an unwieldy language, it's going to take a lot more time to create the programs. There might be a cost learning. There might be an actual cost with the integrated development environment that you're using. There could be a cost associated with runtime checking of your program. In other words, if most of the syntax checking your program occurs at runtime, then it's harder to debug your program because you're only going to find out that you have a syntax error if you execute the code where the syntax error exists, as opposed to running it through a compiler. So it might take longer for you to check and debug your code. There might be a cost associated with the rights to use the language. For example, Microsoft charges for the use of its various programming languages, but Java's free and so is C++. You might think this is silly, but I've experienced this on a number of programming projects. There can actually be a cost, an employee cost for compile time when you're working with large projects. I've worked on projects that literally took, when you wanted to do a build, a local build on your own machine, so you could test out some of your code, where the compile time actually took hours. I wrote a program once to set off a beeper to let me know when it was time to start running my program, because I'd come in the morning and start the compiler to start compiling my code and all the other code in the project, because there were hundreds of people working on the project, and then it would beep maybe 2 hours later or 3 hours later. Then I knew it was time for me to run my program. And I worked on another project at a startup company where there was a similar problem to that. It took like, not hours, but probably about 40 minutes to do a build. So that's just crazy. And finally, if there's any cost associated with the maintenance of the program. And the key here is readability. If it's easy to read code that's been written in the language, then it's going to be much easier to maintain the language. All right. I've got just a few more criteria that I'm going to list here, and I'm going to talk about it briefly, and then we'll be done with characteristics of programming languages. All right. So, whoops. Okay, so the first is portability. If you build software on a particular platform, can you run it on other platforms? If you're doing stuff using Microsoft technology, the answer is no. If you're doing stuff using Java, the answer is yes. Generality. That means, is the programming language itself, does it work, is it a specialized programming language to solve certain types of problems, or is it a programming language that can solve lots of different kinds of problems? So, assembly is really great for low-level, maybe operating system programming. You might need to use it if you're doing certain types of certain parts of a game, but you probably wouldn't want to use it for a very large, complex business application. It wouldn't generalize well in that area. Reliability. Reliability. Are there features that the language itself has that will prevent and handle errors? So there's some really good examples of this. Does the language do type checking at compile time? And if the answer is yes, you've already done some code debugging, and that's done automatically for you. And does the language have any additional features that look for potential bugs before the code actually executes? Aliasing. How does the language handle that? And so we're going to talk more about that in detail a little bit later, but basically this deals with references. Some languages handle references to dynamic types well, like Java does a pretty good job, and some languages do not, like C++, where you have to do your own memory management. Exception handling. does the language have features that are built in that do exception handling, or is that something you have to handle on your own? In Java, there are try-catch blocks and which handle exceptions that are thrown, which is great. But there are some programming languages where there's really no inherent mechanism to deal with exceptions, and so you have to kind of build your own, and that creates a big problem in your code, because you might have one way of handling errors, and then every other developer on your team has their own way of handling errors, and you end up with a really big mess in your code because there's lots of different ways of handling errors. Okay, I think that's good enough for characteristics of programming languages and what makes a programming language good and not good.